15a. Okay, so as with a lot of these questions, you've got like a not obvious method that's quite quick to do, and the more normal obvious method that takes a bit longer. So I'll go through the quick method first. So what we want to do is take this equation, but instead of having x, I'm going to have root x instead, wherever you see x there. And the reason I'm doing that is that, so we know with this original equation the roots were alpha, beta, and gamma. So that means if I stick alpha in there instead of x, then that equation will be true. And what we want is to find an equation where if I replace the x with alpha squared, the equation will be true. So we can see that that works with this one, because if I stick alpha squared in there, you're going to get root alpha squared, which is just alpha. So you'll have alpha cubed minus 3 alpha plus 1 equals 0. And we know that that's true because that's what the original equation is saying. So already we've got an equation with those 3 roots, but we have to turn it into a cubic. So let's play around with it and see what we get. Maybe we'll try expanding that. So root x times root x times root x, that makes x root x. And the problem we have is that we've got all these square roots in here. We don't want to have that, like a cubic equation doesn't have any square roots. So what we might try is keeping all the square roots over one side and move everything else over the other side of the equation, and then we'll square both sides. So I'll move the 1 over to the right, and then I also might factorize the left-hand side, because you've got the root x in each part. Okay, now we can square both sides of that equation. And then I just have to expand this. And I'll move the 1 back over to the left. And there we go. Now we've got a cubic equation, which is what we wanted. So that's the answer. Okay, so that was the not obvious way of doing it. The more normal way, which we're all familiar with, is if you think about a cubic equation having these roots, well, that means that you can factorize it as x minus alpha, x minus beta, times x minus gamma. Because then you can see, if you stick alpha in there instead of x, you get 0 for that part, so that whole thing equals 0. Same thing with beta and gamma. And then to see the connection between this and that, we just need to expand that. So what I like to do, if I'm expanding that in my head, is instead of doing it in the normal sort of order, what you want to do is start with the x cubed, so that times that, and then think about what ways you're going to get an x squared. So you'll have the negative alpha times x. That's going to give you one of the terms with an x squared. Another way would be that x times the negative beta times that x. And then you're going to have that x times the negative gamma. So add those all up and you're going to get that. And then let's think about the coefficient on the x. So we'll have that x times negative beta times negative gamma. So the negatives are going to cancel there and you'll get beta gamma. And then you'll have the negative alpha times that x times the negative gamma. So we get positive alpha gamma times x. And then you also have the negative gamma times the negative beta times x. So if you add all those up, you're going to get alpha beta plus alpha gamma plus beta gamma times x. And then for the constant term, it's just negative alpha times negative beta times negative gamma, which makes negative alpha beta gamma. Now, you don't need to do that expansion every time you see a question like this if you remember that this is what it makes. I sort of do something in between where, like, I know that one of these coefficients will be something to do with alpha plus beta plus gamma and so on. And then I just sort of do this expansion in my head a little bit if I'm not sure which one is which or whether it's negative or positive. So anyway, that tells us, because we can see the coefficient on the x squared here is 0, so we know alpha plus beta plus gamma is 0. We've got a negative 3 on the x, so we know that that's negative 3. And we've got a plus 1 there for the negative alpha beta gamma, so alpha beta gamma equals negative 1. So in the exam, I wouldn't write out that part. I'd just go straight to saying that. Maybe doing some of this in my head. All right, and let's get a clear picture of where we want to go with this. So if we're trying to find a cubic equation with these roots, it means we want to find the coefficients of it, which are going to be alpha squared plus beta squared plus gamma squared is like our new equivalent of this one. So this is what we want to find. We're going to find that, which is going to give us the x squared coefficient. Equivalent of that one, and alpha squared, beta squared, gamma squared. So if we can find these three things, then we'll know the cubic. Okay, so how do we do that? Well, one thing you can see immediately is that if I square that equation, then I'll be able to find that. So I might just number these. So taking equation 3 and squaring it, that gives alpha squared, beta squared, gamma squared equals 1. And then we might get the idea, if we square this equation, that might help us find this. And you don't want to make the mistake that this squared is just equal to that. There's going to be cross terms. If you're not confident about this, I'd suggest actually sort of going back to first principles and writing it out. So I'm taking equation 1 and squaring it. 0 squared is of course 0. And you're going to get the alpha squared from there. And we're also going to get a beta squared and a gamma squared. But then we're also going to get an alpha times a beta, and then another alpha times beta from that one. So you're going to get a 2 alpha beta. And similarly, you also get a 2 alpha gamma and 2 beta gamma. So let's just collect those together. Okay, well, how does that help us? We're trying to find this, and, well, we already know that, because we've got it there, so that's great. So we can just, that bit's negative 3, and then you can shift that over to the right, so you get alpha squared plus beta squared plus gamma squared equals 6. And that gives us another one of the coefficients. And then we might get the idea to square our last equation and see where that gets us. So, very similar to this one, you're going to get each one squared, so an alpha squared beta squared, and alpha squared gamma squared, and a beta squared gamma squared, which that's actually what we want to find there. And then we're also going to get the cross terms, so that times that, and in the same way that we had before. So we'll have the alpha beta times the alpha gamma, so an alpha squared beta gamma, and then also the alpha beta times the beta gamma, alpha beta squared gamma, and then also an alpha beta gamma squared. And that's going to equal that squared, which is 9. So this is what we want to find. So we'll have to figure out what this is. Now you might think, let's factorize that, because you've got an alpha, beta, gamma in each one. So I'm just going to do something here that I wouldn't do on exam, but which I often do in my rough working, which is just to say ditto, because I don't want to write all that out again. All right, let's take the alpha, beta, gamma out. And then you're left with alpha plus beta plus gamma. And that equals 9. Well, this is great now, because we know alpha, beta, gamma, that's -1. And alpha plus beta plus gamma, that was 0. Well, that's even better, so that whole thing is 0. And then we can just say alpha squared, beta squared, plus alpha squared, gamma squared, plus beta squared, gamma squared, just equals 9, because that whole thing's 0. Well, now we've got everything we set out to find. We've got that one, which is going to be like the constant term at the end. So -1 at the end. We have an x cubed. The coefficient on the x squared is going to be the one that's like that. So there it is. And it's negative because of the negative when you do the expansion. And then the other one, the 9, that's going to be the coefficient on the x. So there's our cubic that we were trying to find. That's going to have those roots, alpha squared, beta squared, gamma squared. Part B. So we'll have to use the fact here that half v squared is the integral of acceleration dx. And that's a fact you should probably memorize, but I'll just show you where that comes from. So acceleration is derivative of velocity with respect to time. But if we're thinking of velocity as a function of x, as it is here, so dx by dt, that's the velocity. If that's a function of x, then we have to use the chain rule. So you'd have dv by dx times dx by dt. Now dx by dt is itself the velocity. And one of the really cool things with calculus that you don't really learn at the start is that this doesn't just mean derivative of velocity with respect to time. It's also literally dv divided by dx, and then you can move these things around the equation like you would with any other variable. So we can multiply both sides by dx to shift it over to the left. And then you can integrate. So on the right-hand side there, we've got integral v dv, which is half v squared, plus a constant, but we don't really need that here, because there'd also be a constant on the left. So that's where that comes from. But you don't need to go through that whole thing there, you just need to remember that. Okay, so we've got integral of, that's the acceleration there, minus mu squared on x squared dx. So that'll give us mu squared on x when we integrate that. Now, if that's a little bit confusing, just think of this as minus mu squared times x to the minus 2, and then you add 1 to that, and then divide by the new power, and then that will cancel with that negative. So we get that plus a constant. Now let's think about what that constant needs to be, because you'll notice there's no c in here, it's all in terms of b. So let's work out how that works. So the initial conditions was that it's initially at rest when it's b meters to the right of o. So that means when x equals b, v has to equal 0. So let's plug those values in. So v is 0 and x is b. And that'll let us solve that for c. And then we can plug that back into here. Alright, so we can solve this equation for v now. So multiply both sides by 2 and take the square root. So we're going to get plus or minus square root. So we need to think about, should the velocity be negative or positive? Now it says it starts to the right of O and then moves in a straight line towards O. So it's moving to the left. And that means the velocity has to be negative. And you might want to justify that with some sort of comment out here, like moving to the left. Okay, so we just need to manipulate this until it looks like what we want, which is this. So they've taken out a mu and a root 2, and then they've combined the fractions into one fraction with a common denominator. So we've got that mu squared on both of those. We'll take that out, and the 2, so we get minus mu root 2. And then we have 1 on x minus 1 on b. So we can make a common denominator there. and that'll be b minus x, and there it is. Part 2. So for this one, we want to use a similar trick to what I did before and multiply both sides of this by dt. And we also want to have all the x stuff over one side, so I'll divide both sides by all of this. So that will give you 1 on mu root 2, reciprocal of that. And then you can just integrate both sides of that. So when you integrate dt, that'll just give you t. I'm just flipping this around because we want to find t. And then we need to think about what numbers go here. So what does x start from and what does it finish at? So it starts when x equals b, that was the initial condition. And then we want to finish d meters to the right of her. Okay, now how do we integrate that? Well, they've very helpfully given us this substitution to use. And then we can work out the derivative of that so that we know what to replace dx with. Use the chain rule on that. We get 2 cos theta times negative sine theta. So dx is negative 2b cos theta sine theta d theta. Okay, and then we also need to think about what theta equals when x is b and d. So when x is b, cos squared theta has to be 1, so theta has to equal 0. So our integral will be from 0. And then when x is d, you'll have d equals b cos squared theta. So cos theta will be the square root of d over b, or theta is arc cosine root d over b. So that's where that comes from. And we've still got the minus 1 on mu root 2. So b times x is b squared cos squared theta. And then we've got b minus b cos squared theta. And then we need to multiply by all of that, so need some more room there. Times negative 2b cos theta sine theta d theta. Now that negative will cancel with that. We've got the 2 divided by root 2 makes root 2, and let's actually bring that out the front. So we'll have a root 2 over mu. So I've just combined that 2 and all of that and taken it out. Okay, and on the bottom here, you've got a b times 1 minus cos squared. So that's b times sine squared. And yeah, I would probably sort of do a lot of things in one step, but I'll slow this down so that you can actually see what I'm doing. And then we've still got the b cos theta sine theta d theta. Okay, so we can cancel that with that. And we've got a root b from there and the b there. And then I might bring that out the front. So we've got root cos squared on sine squared, so just cos on sine, and then that'll cancel with that sine. So we're left with cos squared theta d theta. Let's just check where we're trying to get to. Oh, okay, they've put the b inside that same square root with the 2. So I should do that as well. And mu, and then you get the idea, just that again, and then that's what we were trying to prove. So that's it. Part 3. So what we're looking for here is for d to be approaching 0, because d was the end position of the particle. So what we want is the limit as d approaches 0 from the right of t. Okay, so we get this bit will just be 0 if d is approaching 0. And then we've got b times the arc cosine of root 0 over b. So arc cos of 0 is actually pi on 2. So we get b times pi on 2. And then we just need to simplify that. So there's a few ways that you could state the final answer. We've got b times the pi on 2 mu times root b on 2. So I've just collected those there and that there. Or if you like, you could split this into like root b over root 2 and then combine the two fractions. So we could have like b root b times pi over 2 root 2 mu. Either one of those is fine. Part C. Okay, so we want to start by assuming that we don't know what any of these numbers are, and we're going to derive them. So we're just going to have a on x and b on x plus 1, c on x plus 2, and d on x plus 3. And then we have to solve for these. So what we're going to do is multiply both sides of the equation by all of this. So the a on x times all of that, that x is going to cancel with that, and there'll just be these left. And then for the b on x plus 1 times that, the x plus 1 is going to get cancelled out, so we're left with those ones. And the same sort of thing for the rest of it. Run out of space. Okay, so then what you want to do to work out a, b, c, and d, this looks really complicated, but it's not too bad, because what we can do is we could say, let's suppose x equals 0. And then this is going to disappear, that's going to disappear, that's going to disappear. So you will just have the 3 factorial, which is 6, equals, and then just this one. So a times, that'll be 1, and 2, and 3. So that's a times 6, so a has to be 1. And then we might set x to be negative 1, so that all the terms with an x plus 1 in them are just going to be 0. So we'll be left with this one. So that makes b times negative 2, so b will be negative 3. And then we can do x is negative 2, and that'll knock out all of that one, and that one, and that one, any of the terms with the x plus 2 in them, because they'll be 0. So we just have that bit left. So c times negative 2 times negative 1 times 1. So that'll be positive 2. So 6 equals 2c, so c will be 3. And then the same sort of thing to get rid of all of that and just have that one left. So that's positive 6 and then times negative 1. So 6 equals negative 6d, so d is minus 1. Minus 1. And that, luckily, is what we were trying to show, that a is 1, b is minus 3, c is 3, and d is minus 1. So that's it. Part 2. Okay, so for this one, we're going to do pretty much the same thing as we did in part 1. We're going to multiply both sides by this denominator and cancel stuff out. So like that one times this, the x's will cancel. And what we want to do, so we're trying to find AK. We're interested just in this term and not in the others. When we multiply that one by that, the x plus k is going to cancel with the x plus k in here. And so what we want to do is set x to be minus k, because this is the only term that's not going to have the x plus k, because that will have cancelled. And that'll make all the other ones 0, because all the other ones will have an x plus k in them. So it's kind of hard to set this one out, because like we obviously can't write all these out. What I might do is just say, I mean, we don't really want to write all this other stuff out. The only relevant part of it is that they all have an x plus k in them, and this one doesn't. So what I might do to show that, so after we've multiplied both sides by that, you'll just have these bunch of terms that have an x plus k in them, and that's multiplied by, you know, whatever, we don't really care, all of that stuff. And then we're going to have the AK times x plus 1, and then times everything up to, because the x plus k will cancel, we're going to have everything up to x plus k minus 1, and then we'll be missing the x plus k term, and then we'll have the next one, which is x plus k plus 1, and times everything up to x plus n. And then we're going to say let x equal minus k, and we'll have n factorial equals, now this will be 0, so I can just put a 0 there. So the x is minus k, then we've got a minus k plus 1 times and so on up to minus 1 if x is minus k. And then there's this bit, so we've got, that'll just be 1, and then there'll be a 2 and so on up to the minus k plus n. Okay, now you also might want to, if you're getting confused about where you need to be going with this, you might want to have an idea in your head of where we're going. So maybe think of another way of writing this that we can turn that into. So n choose k, that was meant to be a k, not an h. N choose k is n factorial over k factorial times n minus k factorial. And so you might also want to, like if you're still confused about what to do from here, you might want to rearrange this so that it's like n factorial equals. So this would give you, so like multiplying both sides by that and dividing by that, you would have a k, have the k factorial and n minus k factorial. And 1 over that is actually the same as just minus 1 to the k, because like 1 over minus 1 is the same as minus 1, and 1 over 1 is the same as 1. So we're hoping to turn this into that. So it's good to have an idea of, in your mind, of where you're going. So you can work backwards from the goal as well as forwards. So we're going to need a k factorial. Well, that's great, because you've got k times, except that it's got these negatives. So you can think of this as, you'll have a negative 1 times k, and this is negative 1 times k minus 1, and so on down to 1. So that's going to be like negative 1 to the k times k factorial. And then this bit is 1 times 2 times and so on up to n minus k. So that's n minus k factorial. Okay, well that's great, because that's now the same as that. So now we just need to rearrange this. Like, this isn't part of your working, this is just in your mind or on your rough working. So now we just need to turn it into that form, so divide both sides by all of that. So ak equals n factorial on k factorial n minus k. And then that's, yeah, you can basically just say that as your next step. And there it is. Part 3. Okay, I think the hardest part of this question for most students is just figuring out how do I use part 2, that result, to show this. So let's actually take a closer look at what we actually proved in part 2. Now this formula is actually a formula for each of these little A0 and A1 and so on that we can plug in. So let's write that out properly. So from part 2, n factorial on x plus 1, so on up to x plus n. It's equal to a0 is now negative 1 to the 0 times n choose 0 on the x. And then we've got a1, which is negative 1 to the 1 times n choose 1 over x plus 1 from there. And then and so on up to the an, which is negative 1 to the n times n choose n over the x plus n. Okay, that's great. So now this is really good because we've got an n choose 1 there and there's an n choose 1 in the thing we're trying to find. So how are we going to get that? Well, this thing has all these x's that aren't in here. So what are we going to do about that? Well, we want to have a 2 in the denominator here. So if we just set x equals 1, that's going to be really good. And also you can see we're going to have an n plus 1 there, which is what we want to have there. So let's see what happens then. So we're going to have 1 times, that'll be 2, and so on up to 1 plus n. Negative 1 to the 0 is 1, and n choose 0 is also 1, and then that x will be 1 as well. Okay, and then we've got a negative 1 to the 1 is just negative 1, so we'll have like a negative n choose 1 over, that'll be 2, and so on up to, we don't really know what negative 1 to the n is without knowing what n is, so we'll just leave that as negative 1 to the n. N choose n is 1, so that'll just disappear over n plus 1. So now this is really good. This is looking a lot like that. We just need to just simplify it a little. So that's 1. Let's put that into the same form as that. So bring the minus out the front and have half times n choose 1. And then that's the same as that, so that's fine. We don't need to change anything there. Okay, and now let's think about the left-hand side. So n factorial is like 1 times 2 times so on up to n. And then this is the same thing, but then also times the n plus 1. So all of that stuff will cancel with that, and we're just left with 1 over n plus 1. So that's great. We've shown what that equals. And now it's asking for the limiting sum. So that means like as we get more and more terms of these, like as n tends to infinity, what's this sum going to equal? So we can just say like as n tends to infinity, 1 on n plus 1, what's that going to do? Well, that's going to be a really big number on the bottom, so this is going to approach 0. So that's the limiting sum.